Hello. In this short presentation, we want to show, using a piezoelectric example, how to set up a simulation in NACS for an ultrasonic thickness sensor. This is the model that we are using. We have here a piezoelectric sender that will launch an acoustic wave resulting from a voltage excitation. That wave will travel to a solid media, will be partly reflected, partly transmitted through that medium. The vibrations will be initiated, and finally another acoustic wave will be launched on the receiving side and will be received by the receiving transducer. The solid media itself should be infinitely extended in that direction. So to sum up the components, we've got the piezoelectric sender right here, we've got the adaptation layer on the sender side, we've got the solid media at that point, we've got the adaptation layer at the receiving side, the transducer at the receiving side, and finally the air volume surrounding all of the mentioned components. Here are some dimensions that have been mainly interesting for the first part, where we generated the geometry and the mesh for our simulation. Right here we can see the material data we will use later on. So we've got the piezoelectric transducers made of PCT5H. We've got the adaptation layers made of polyurethane. We've got the solid medium should be made of paper. And finally, in our acoustic domain, we are using air. We want to carry out a transient simulation. Therefore, we can use a sine burst. Excitation frequency will be 25 kilohertz. We will use 5 periods. We'll use the first and the last period for fade in and fade out purposes. The resulting signal is depicted right here in the time domain and the frequency domain representation. We want to obtain some results from that simulation. On the one hand, the acoustic pressure, on the other hand, the mechanical displacements, and finally the receiving voltage signal. So that's all at that point. And now we will start with the hands-on. So this is the graphical user interface of NACS. On the left-hand side we can see a navigation pane, and what we're gonna do right now is we will load a mesh file previously generated. So this is the mesh we want to use. Then the mesh is loaded by NACS, and we can see on the left-hand side a certain list of regions, a certain list of groups, and here on the right-hand side is depicted a graphical representation of our simulation model. So what can we see? We've got that air region, as already mentioned before. We've got the paper, we've got the receiver adaptation layer, we've got the receiver piezoelectric device, we've got the sender adaptation layer and the sender device. And here's a certain set of groups that may be used later on. At first we will start by defining a Cartesian coordinate system for our piezoelectric devices, since we need to have the 3 direction of the material pointing an orthogonal direction of the electrodes. So we will define a coordinate system with a certain rotation angle. So this can be easily verified here, as already said before. It should be 30 degrees. Right now we can see that there is a certain difference. It doesn't seem like 30 degrees were used as described in the model setup. So the angle here is used for that mesh file is 25 degrees. This could be easily verified using that preview of the coordinate system. Okay, so right now we define the coordinate system. Next step is to assign the materials to our regions. The region air, of course, has material air as well. The region paper has the material paper. The receiver adaptation layer should be made of polyurethane, and our piezoelectric devices should be made of PCT5H. Now, this was a little quick. We of course have to assign a material rotation system. Here we can select our previously defined coordinate system, and right now the 3 direction of our material is pointing in orthogonal direction to the piezoelectric electrodes as we want to have it. Okay, so we're ready with the material assignment as well. Now we have to tell NACS what we want to do. A new analysis step. We want to do a piezoelectric acoustic simulation and a transient one, of course. At first we have to define the time step size. So here we have a frequency of 25 kilohertz. We want to discretize with 20 time steps per period. So we will finally arrive at something like a time step size of 2 microseconds. And we have 5 periods that correlates to 100 time steps. Let's say we take another 100 time steps for the traveling of the wave through the air. So this is the setup for our transient simulation. Next step is we have to define regions to our analysis. So in the mechanical domain, NACS already recognized that those are the possible regions. We're using the paper and the 2 adaptation layers in the mechanical domain. In the piezoelectric domain, we are using the remaining 2 piezoelectric regions. And so one thing still left. This is the setup of the acoustic regions, and this is in that simple case just our air region. Now here everything is all set up. In the region settings we could, for example, modify the grid order we are using internally in that simulation, but this can be discussed on another point. Now the coupling, we just have the mechanic acoustic coupling. Here we can select our fluid structure interfaces. This will be on the one hand the interface of the paper on the lower and the upper side of the paper. Here we can see it just a little bit. Those are 2 surfaces, and then we've got a fluid structure interface here on the receiver side and also on the sender side. So this is the setup of the coupling. We don't have any nonlinearities that we have to take into account. Damping, we could specify that we want to use some kind of damping in, for example, our adaptation layers. And let's say this damping should be valid between 10,000 and let's say 30,000, so 10 kilohertz to 30 kilohertz. And what we can see right here is the resulting loss tangents delta in our frequency region, depicted right here as red a patch, and in our material of the receiver and the sender active part region, adaptation layer region, we have that tangents delta set to something like 0.5%. And the result of the damping from the Rayleigh damping definition will be the blue curve. So it will be something between 0.55 and let's say here 0.48% of the tangents delta. Okay, we can also activate softening, so to reduce the effects of the mechanical locking. So this will result in additional shape functions that will finally result in a softer material. There won't be an error by using just first order elements as used in the discretization of that geometry. Then we have to set up the boundary conditions. Here we start in the mechanical domain. We want to define absorbing, so free field boundary conditions at the paper bounds. So this is here on both ends of the paper. Then we want to add acoustic free field boundary conditions also on the air boundary. This is done right here, and so also the air is all set up. Then one thing still missing is the electric boundary conditions. So we have electric ground potential on the, let's say, receiver bottom electrode and on the sender bottom electrode. Then we want to define our excitation. This should be a voltage excitation, so we prescribe the electric potential on the sender top electrode. And as already mentioned before, we want to use a sine burst, and here is a signal editor that allows us to set up certain functions, and here we already find a sine burst. Here are the parameters already depicted. Frequency should be 25 kilohertz, 5 periods, 1 period for fade in, 1 period for fade out. We press return, and so we can see the resulting signal already in our here specified time range with the discretization already chosen. If we would choose something else, for example, let's say 250 kilohertz, we can easily see that this cannot be really computed using the setup we've chosen. If we would use something like, let's say, 75 kilohertz, that would be possible, but the side lobes and the frequency representation are already quite high, and we can already see that here the representation of the time signal isn't that appropriate anymore. So we've been choosing 25 kilohertz, and so we save it right here and press apply on this side. So one thing still missing, these are the equipotential. It's on the receiver top electrode. This is where we want to obtain the electric voltage signal later on. So the boundary conditions should be all set up. Next step is to define the results. Here we want to have in the mechanical domain the mechanical displacement on all regions available. Then we have in the acoustics domain the acoustic pressure, just in the air region. And then we want to obtain the electric potential on the sender top electrode. And this is something we don't want to get this as visualization results so that we can see it finally in the postprocessor. We want to obtain this history result so we can see the result in an XY chart voltage over time. Okay, so that's all. So here we can still specify if we want to use implicit time stepping or explicit time stepping. So in case that we would use an explicit time stepping scheme, then NACS would automatically compute the possible maximum time step and compare it with the time step we've chosen. And for this discretization found here, the time step would be much smaller than this one that we specified, though this wouldn't make any sense for this setup. The explicit solver, of course, is much faster, therefore it might be reasonable to use it, but in that case we cannot use it. So we finally just save our simulation, so here with verbose parameters. There are already some simulations available, so maybe we could just call it 25 kilohertz today. And then we here can choose the license that we want to use for the computation. We have 8 cores available, let's just use 4. Then we press save and start, and then we can see in the lower picture right here that NACS starts the simulation, and after the third time step we will see how long the simulation will still take. Let's see what NACS will tell us how long we have to wait. So this is gonna be something like a little more than a minute. In a short amount of time we will see right here something like the resulting remaining time, so still 57 seconds are left. This is enough time to take a look on at first the material editor and then also the job control. Let's start with the material editor. We've been using some different materials. We had the air, for example. Here we can see general properties of the air, damping properties, acoustic properties, so the speed of sound or the bulk modulus can be specified. Also magnetic properties are available. For our paper, for example, we have different properties available here. The damping, the tangent delta is specified with .4 at a measured frequency of 100 kilohertz. Here mechanical properties may be specified. Here we've been choosing an isotropic material behavior, and this can be specified using Young's modulus and the Poisson ratio, or Young's modulus and shear modulus, long and transversal speed of sound, or the Lamé parameters. And you can see that Even that you enter just Young's modulus in the Poisson ratio, you get also an impression on the longitudinal and transversal speed of sound of your material, for example. Finally, we have the piezoelectric devices, and here we can see the piezoelectric tensors. So those are specified in the stress charge formulation, stiffness tensor, coupling tensor, and also the permittivity tensor. If you're more familiar with the strain charge formulation, so it just can be converted and you can easily set up the material in the formulation that you're used to. So here we can see the job control itself. We can see the job that we've been previously adding. The job is right now finished. We can see right here the log of that next job. You can here easily add new jobs. You can delete jobs from that queue. You can start jobs. You can stop jobs. You can continue jobs you've stopped before. And there's also a simulation queue. That means you can set up a certain number of cores that the job control may consume of your machine, and then the jobs in that job list are simulated one after another until everything is finished. So we want to right now step to the post-processing. Here we just select our job that has been running and we press the post-process button. So this is the result file. It's loaded and we can see the model that we already knew before, where it looked something like that. Right now we want to step to the electric potential result that we are mainly interested in. So we can see right here the result selection. So in the first multi-sequence step, we've got the result electric potential on the entity receiver top. And this is what we want to see. It looks like that. We can also easily turn on a grid. We can zoom into that signal. We can again easily zoom out of that signal. And we can also change right here the representation to, for example, frequency domain representation. What we can see in that small region is that we set up an excitation at 25 kilohertz. Right now it looks like the main focus is around 23 kilohertz, so this is mainly due to some kind of piezoelectric and mechanical interaction. So this everything concerning that receiver signal that we've been interested in, but of course we want to also to see what happens in the other domains, for example concerning the mechanical displacement. So this is the result in the first time step, depicted right here at time 2 microseconds. We could forward a little bit and you can see that here something happens. Also on the paper we can resize our color, our result range right here. But of course we want to see something at the paper, so we can deactivate, for example, the complete sender, and then we can see what happens right here on the paper. Of course we can also deform that geometry. Using that slider you can easily see what will happen right here. Next thing that is of interest is also what happens in the acoustical domain. Here we are using some isoplots for visualization. Here we also use a calculator to compute another quantity, and what we compute is the sound pressure level. So this is the sound pressure normed to the hearing level, and this is at 20 micropascal. Take the logarithm with base 10 multiplied by 20, and so you arrive at the sound pressure level. Right now we want to obtain some isometric surfaces. Our range is currently between 22 and 82, so let's see what happens at something around, let's say, 75 dB. Not too much, let's get a little less, still not too much. So here at 65 dB, yeah, that looks like we can see what happens in the acoustical domain. Now only on the upper half, of course, due to the paper in between, we've got a double impedance step, and that means that the acoustic sound pressure levels will be much less on the lower half. We could add another ISO level at, let's say, 35 dB, and so we can also see something on the receiver part. If we want to get rid of those artifacts on top, we could also use this clipping plane, for example, to just clip things away that we're not interested in, and it would more or less look like, yeah, it's, let's say, like that. It isn't perfect, but it helps a little. So we deactivate our clipping plane, and so we press the play button and can finally see what happens right here. The acoustic wave is traveling in that direction. We can also see that a mechanical wave is traveling on the paper, and it doesn't seem like it is reflected here on the paper bounce as we wanted it to be. Okay, so this is mainly everything that I wanted to show in the post-processor. We've been seeing a piezoelectric thickness transducer that is emitting an ultrasonic pulse, and here we can see the simulation result in the acoustical domain, in the mechanical domain, and also here the resulting voltage. So thanks for watching, and see you next time. Bye.